Hello everyone. Our team members are Yehong Zhang, Bowen Ye, and Tong Wu. In this presentation, I will explain the regression modeling process implemented in my Python notebook for predicting medical insurance charges. The focus of this discussion is not only on achieving strong predictive performance, but also on understanding how model performance improves through systematic experimentation and how model fit is diagnosed using validation techniques. In particular, I will explain how pre-processing decisions, model selection, cross-validation, and learning curve analysis were used together to determine whether the final model is underfitted, overfitted, or well-fitted. I will also reflect on how these evaluation strategies can be extended to real-world machine learning problems. So the objective of this project is to predict individual medical insurance charges using regression models. The dataset includes demographic and behavioral features such as age, BMI, smoking status, region, and number of children. These variables are known to influence healthcare costs and contain both linear relationships and nonlinear interactions with the target variable. One important characteristic of this dataset is that insurance charges have high variability and are right-skewed. Because of this, minimizing training error alone is insufficient. The primary goal is to build a model that generalizes well to unseen data, meaning that validation performance becomes more important than training performance when selecting the final model. The first stage of improving model performance involved careful pre-processing. Missing values were handled to ensure that models received complete input. Categorical variables such as smoking status and region were transformed into numerical representations through encoding, enabling regression algorithms to interpret them correctly. Next, feature distributions were examined. Since the target variable insurance charges exhibited strong right skewness, transformations were applied to stabilize variance and reduce the impact of extreme values. This helps regression models learn more consistent relationships rather than overemphasizing outliers. Feature scaling was also applied when appropriate. While tree-based models are less sensitive to scale, linear and distance-based models benefit from normalization because it improves optimization stability and ensures fair comparison across algorithms. These pre-processing steps reduced noise, improved numerical stability, and created a more reliable foundation for model comparison and evaluation.
So next part is model selection and performance improvement strategy. To improve predictive performance, multiple regression models were evaluated instead of relying on a single approach. Linear regression was initially used as a baseline due to its interpretability. However, because healthcare costs are influenced by nonlinear effects and feature interactions, tree-based models such as decision trees, random forest, and gradient boosting were also tested. Hyperparameter tuning was performed to control model complexity. Increasing complexity can reduce bias, but may increase variance. So parameters such as tree depth and learning rate were adjusted to balance this trade-off. Cross-validation plays a crucial role in model selection. By evaluating performance across multiple folds rather than a single split, cross-validation provides a more stable estimate of generalization performance and reduces the likelihood of selecting a model that performs well by chance. After comparing validation metrics across models, the gradient boosting regressor achieved the best balance between predictive accuracy and stabilities. Next part is assessing model fit using learning curves. To determine whether the model was underfitted, overfitted, or well-fitted, we analyze learning curves that plot the training error and validation errors as function of training set size. A learning curve provides insights into model behavior. If both training and validation errors remain high as more data is added, the model is underfitted because it lacks sufficient complexity. If training error is very low but validation error remains significantly higher, the model is overfitting, meaning it memorizes training data but fails to generalize. A well-fitted model typically shows training and validation errors converging toward similar values as the dataset grows. Learning curves that don't just vary in shape based on the model, they also reflect real-world conditions. For example, overfitting often shows up in a small dataset or when the model is too complex for the data. Underfitting might happen when the features are too simple, or the model is too constrained. I've seen both patterns in my experiments, depending on how I pre-processed on the data or turned the model. In this project, the best performing regressor demonstrated relatively close training and validation RMSE values, indicating a balanced bias variance trade-off. Additionally, cross-validation results were consistent across folds, suggesting that performance was stable and not dependent on the specific subsets of data. During experimentation, when larger gaps between training and validation error appeared, model complexity was reduced or regularization effects were increased. For example, limiting tree depth or adjusting minimize simple parameters helped reduce variance and improved generalization. Based on both learning curve behavior and validation consistency, the final model can be considered well-fitted.
Next, our project highlights that diagnosing model fit requires combining multiple sources of evidence rather than relying on a single metric. Training error alone may suggest strong performance, but without validation analysis, it can hide overfitting. And the learning curves provide a dynamic view of how models learn as the data increases, while cross-validation ensures that conclusions are not dependent on a particular data split. Reflecting on this process, we recognize that model evaluation is iterative. In future work, we would extend this approach by incorporating residual analysis to identify systematic prediction errors and using interpretability methods such as sharp values to verify whether learned relationships are meaningful rather than coincidental. So developing a structured strategy for diagnosing model fit is essential for deploying machine learning models in real-world decision-making environments. So in summary, the regression model's performance was improved through systematic pre-processing, model comparison, and validation-driven refinement. And the learning curves and cross-validation demonstrate that the final model achieves a balance between accuracy and generalization, indicating that it is well-fitted rather than underfitted or overfitted. That's all. Thank you.